What I wanted to discuss with you in this video is something called the Moivres Theorem. Now this is a very important theorem that we work with when we're doing calculations with complex numbers written in polar form. What we have to be able to do with it is understand what it means, be able to prove where it comes from, and then be able to utilize it effectively when we're working through tasks involving the polar form of complex numbers. Now, it originates from a mathematician called Abraham de Moivre. He lived from 1667 to 1754. He's a French mathematician, and he actually lived in London. He escaped religious persecution, lived most of his life there. And he was good friends with Isaac Newton and James Stirling. Now, he looked at two key notable areas of mathematics: probability and the connection between complex numbers and trigonometry, so looking at polar form. And one of his most notable pieces of work looked at powers of complex numbers and the relationship to each other. And in this research, he came up with what we know as the Moivres Theorem. Now, the Moivres Theorem states that if we have a complex number z in the format r bracket cos theta plus I sin theta, then z to the power of n equals r to the power of n cos of n theta plus I sin n theta. Now, initially he proved this for any integer, but later extended it for any real number out there. So this is the Moivres Theorem, and this is what we need to be able to work with, or we need to be able to utilize. It makes our calculations with complex numbers in this format a hell of a lot easier than we're used to. Now, one thing we have to be able to do, though, is understand where it came from, and ultimately, and ideally, be able to prove it. So how do we do this? Well, let's imagine that we have some sort of natural number n equal to k, so let's call it that, for which the theorem is true. So it's true for some value. So what that then means is that z to the power of n equals r to the power of n brackets cos n theta, plus I sin n theta is true for some value. So let's imagine the theorem holds out. Let's then look at the next number. So let's imagine we raise the power an extra 1 and we look at z to the n plus 1. Well, that's going to be the equivalent of z to the n times z. Now, z we've already said is in this format here. So what that means is we've then got r to the n cos of n theta plus I sin of n theta. So that's our z to the power of n, and that's going to then be multiplied by the z from the previous form, which is times r bracket cos theta plus I sin theta. Now, if we then multiply out these brackets, so we'll group the r's together in front, so that's going to be r to the n plus 1. Great, that's kind of what we were after anyway. And let's multiply out the brackets. We'll end up with cos n theta times cos theta from our first term. We're then going to get a plus I sin n theta times cos theta. We're then going to get a plus I sin theta cos n theta. We're then going to get a plus I squared sin n theta sin theta. Now, if we just focus on this bit in the bracket here and group the real and imaginary parts together, we've got cos n theta. Cos theta is the first real part. Now this bit here, I squared sin n theta sin theta. Well, remember, I squared is negative 1, so there's our second real part. That's then take away sin n theta sin theta. So that's the real part. If we then group the other two bits together, we get our imaginary part. So that's plus I, and we'll put that in a bracket, sin theta cos n theta plus cos theta sin n theta. So we've got the real and imaginary parts together. Now we can look at both of these. This first one here we know that that can be written as cos of n plus 1 times theta. And this one here can be written as sine of n plus 1 times theta. So what that then means is we've proven it for the next value of n. We've proven it for the next value in our sequence. So if it's true for n equal to k, which you've just shown here, and if it's true for the next value, we're near enough there to prove it by induction. What we have to do though is show that it works for the very first value, i.e. if n equals 1. So z to the power 1, that's just z, which is equal to r cos theta plus I sine theta. Now that takes the format we want. Only difference is the power here is 1, great, and the n's in both of these are 1, so it just gives me theta. Great. So we've used proof by induction to show that it's true for the first value, it's true for a generic value n equal to k. We then look at the next value up, and it's true for that value, so it's true for all values within the natural set of numbers, i.e. all integer values from 1 and above. So we've proven it for that. Now, de Moivre went a bit further. He managed to prove it for all real numbers. This is beyond the scope of what we want to be able to do at this point in time. There is a way to prove it, and if you look it up and you're interested in it, go for it. The key thing we have to be able to do is remember this sort of proof here and actually then be able to utilize it and work with it, performing calculations with what we've got here. Let me show you a couple of examples. So first one, if I give you z equals 1 plus I times root 3, let's imagine I ask you to find these three powers here. So I first want you to find z squared, z to the 5, and z to the power of 10. Well, first thing we have to do is write the z in polar form. So remember, for z to be in polar form, we want r bracket cos theta plus I sine theta. Now remember, to get r, that's the modulus of z. So that's going to be equal to the square root of 1 squared plus root 3 all squared. So 1 squared is 1, root 3 squared is 3, so it's the square root of 1 plus 3, which is 4. So the modulus r is equal to 2. We then want theta. We know theta is equal to tan minus 1 of y over x. Y represents the value associated with our imaginary part of the number, x the real part. So in this case, it's going to be tan minus 1 of root 3 over 1, so just of root 3. So if we were working through with that, tan minus 1 of root 3, figure it out, gives me pi by 3. So from that, I can say fine, so in polar form, z is going to equal 2 bracket cos of pi by 3 plus I sine of pi by 3. So there we go. We've got our z written in polar form. We can now utilize it in each of these calculations here. So let's look at part A. So part A, we want z squared. So we know z squared, following de Moivre's theorem, is going to be 2 squared bracket cos of 2 times pi over 3 plus I sine of 2 times pi by 3. So that's following the format of de Moivre's theorem and how we want it. We then simplify it. 2 squared, well, be worried if you didn't know that was 4 by now. So it's going to be 4. Sort this bit in here. We get cos of 2 pi over 3 plus I sine of 2 pi by 3. Now, a key thing to note here. Remember, when we were looking at polar form, what we said was that the range for theta had to be existing between pi and negative pi. If this here is out with that range, you then have to subtract 2 pi or add 2 pi to bring it back within that range. So it's a valid answer. So if we take z to the power of 5, for example, that's going to equal 2 to the power of 5 bracket cos of 5 times pi over 3 plus I sine of 5 times pi over 3. If I then work that through and calculate it all out, 2 to the power of 5, that's 32. I'm then going to have cos of 5 pi over 3 plus I sine of 5 pi over 3. Now, 5 pi over 3 is out with that range. So what I've got to do is I've got to subtract 2 pi from it to bring it back within this range that we've got here. So if I do 5 pi over 3, take away 2 pi, that's the equivalent of 5 pi over 3, take away 6 pi over 3, so that's negative pi over 3. So if I substitute that in, that gives me 32 bracket cos of negative pi over 3 plus I sine of negative pi by 3. Now remember our rule from previously, the cos of negative pi over 3 can just be written as cos of pi by 3. This here, to get rid of the negative here, this ends up becoming a negative itself. So we end up getting 32 bracket cos of pi over 3 take away I sine pi by 3. So that's that one written in the format we want. And again, we've just used the Moivres for it. Now again, we can use the Moivres theorem for part C, regardless of how high the power is. We just have to remember this key step, like we did here, of taking away to get back in the range. So let's look at C. So I want z to the power of 10. Again, same set of steps. We've got 2 to the power of 10. We're going to then get cos of 10 pi over 3 plus I sine 10 pi by 3. So sort this out then. 2 to the power of 10. 2 to the power of 10 is 1024. What we've then got is cos of 10 pi over 3. Now again, we have to bring it back into the range of negative pi and pi. So I'm going to take 2 pi off of that. So I'm going to do 10 pi over 3, take away 2 pi, so take away 6 pi over 3, which is going to give me 4 pi over 3. Oh sugar, that's still out with our range. So guess what? We take away another 2 pi. You keep taking away the 2 pi until it brings it back into the range that we want. So if I then take away 2 pi, again from that, what I end up getting is negative 2 pi over 3. Then I can simply substitute it into there and simplify it the way I want. So if I substitute it into here, I get cos of negative 2 pi over 3 plus I sine of negative 2 pi by 3. Using the same rules as this previous example, we can get rid of the negatives. 1024 bracket cos of pi by 3, cos of 2 pi by 3, sorry, take away I sine of 2 pi over 3. Now, quick point to note, each of them I've left in polar form. Quite a lot of the time you'll then be asked to put it back into the standard form for a complex number, so back into this form. So if I were to go back and change each of these into that format, the first one I would end up writing as negative 2 plus 2 root 3i. The second one here, the 32 cos pi by 3 take away I sine pi by 3, so my z to the power of 5. That would end up giving me 16 take away 6 root 3 times I. And then the last one, the one that we just did there, that would end up giving me negative 512 take away 512 root 3i. So there you go, that would be them written in the standard format for complex numbers. So just be aware of how they want you to write the final answer. To be honest with you, 9 times out of 10, that'll be how they want the final solution written in that standard format. So using the Moivres theorem, that makes these calculations a lot easier. Rather than going through the process of multiplying out several brackets, one after the other, use this, work it through, make your life a lot easier for yourself, and make the calculations as simple as you can.